All right, so this is Discrete Math, spring 2021. My name is Scott Grizzard from the University of South Florida. The YouTube stuff finally got posted today. The thing was horrible. Also, the live backup stream, you can hear me, but you can't see me yet. Give me a moment and I'll fix that. So let's see. Now I'm trying this. So we have a live. Okay, so if you're in the live backup stream, double click on the thing that says live. So if you didn't work, if Twitch is not working for you, go to the live backup stream class and double click on my name where it says live, and you should be able to see me. I think that's it for that. So we're going to try this. We're going to see if it works. Apparently people that are behind the, yes. So you can ask questions on Twitch. You can ask questions in Discord. Twitch questions are public. Discord questions are private. If Twitch is working for you, please use Twitch, because there's only so many people that can be in the live stream on Discord at the same time. So if you can use Twitch, please use Twitch. If you can't use Twitch, hanging out the stream is fine. Okay, so that's the management. Also, I posted an announcement about with some management stuff in it about how we're going to do makeups. I said I'll have them up this weekend. I'm very happy about the fact that it turns out we have the software. I can use that software for this class. I didn't know if they had bought only so many copies of it or not. Yes, so you can. It doesn't matter where you are watching. You can ask questions at the other space. So if you're on Twitch, that's awesome. Perfect. You can still ask questions in Discord. Polls will still be in Discord. Laura will still be in Discord and to help as the TA. And so it doesn't matter which one you're in to ask questions in Discord. You can do it from Twitch or from Discord. All right. So that's it for the kind of the maintenance. Let's go ahead and talk about this quiz. This would be quiz 1B. Oh, one other thing. You guys are sending me emails. That's awesome. I have a ton of emails. No promises on getting back to you right away, but I'm trying. But on the emails, please send me, if you are sending me, try not to send me a message through Canvas's email system. Send me, go to your email, your USF email, the Outlook or whatever it is thing, and send me a message from there, please, to my email address. The reason why is I am the coordinator for all of I'm one of the coordinators for the peer leading for calculus, which means I'm an instructor on all the calculus sections Canvases. So every time someone sends a message in calculus to the instructor, I get a copy of it. That's, all the calculus classes, not just the ones I'm teaching. I mean, all of them. So if I've got filters set up and all that, but sometimes your questions your messages will get missed. So please use the email system because I'm not always perfect about getting stuff through the Canvas system. Okay. Also, people were asking me about a list of readings before the lectures. You guys are much more organized as students than I am. I'm a horrible student. So I don't really have a list because this is not the same textbook we used last semester. So I don't have a list of the things. That would be nice. And if I have time to set it up, I will, but no promises. It's still, it's just there's too much going on in this semester for me to be able to promise you the readings beforehand. I will try, but no promises on it. Okay, so let's talk about the quiz. Yes, the teacher can be a horrible student. This is what makes the teacher a good teacher, because the teacher is a horrible student and understands horrible students. Most teachers don't understand horrible students. But I do, because I am one. Okay. Yes, I will be posting these. Yes, you can take the retake, even if you missed the quiz. If you missed the quiz, this for the first 2 weeks of Zen, you get full credit. After the first 2 weeks of Zen Dudism, you'll only get half credit. So retakes are only half the points you meet after the first week, after the first 2 weeks. Okay, how many different messages can be encoded in 16 bits? This is the same formula we had last time. It's 2 to the 16. Okay, 1 to 5. How do we feel about that one? Okay. All right, so let's let A equals 0, 2, and 4. So this element, the size of A is 3. Now the book is using this. This is mine. The book is using this pound symbol thing. I don't like that. I mean, I really don't like that. But that's what the book uses. This isn't even a function notation here or anything. It's just that. Okay, I'll just mention that's what's going on with the book. I don't really like that symbol. I prefer the absolute value signs. The absolute value signs, by the way, are standards, as the standard. So if you're looking up stuff in algorithms and stuff, you're more likely to see this absolute value thing used for cardinality than this thing. I'm using what is the more standard, the more modern notation. The book likes the pound sign. Good for it. Now this 2 to the A business. This is a list of the subsets of A. Okay. Okay, so the list of the subsets of A, let's see, the empty set. The set containing 0, the set containing 2, the set containing 4, the unordered pairs 0, 2, 0, 4, and 2, 4, and then the set itself. Or the triple. I don't know which one I put it on. Okay, so 1 to 5. How do we feel about that? Okay. All right. Any questions about that one? Yeah, so you could also write the whole set out. So I could have written this instead. It's the exact same thing. Right, so this equals A. These are the same thing. What's the cardinality of 2 to the A? That's 8, right? It's 2 cubed, which equals 8. Now, what is the cardinality of the set containing A? There's only one thing in it, right? The outermost thing, the outer set, has only one thing. That's right. How do we feel about that one, 1 to 5? Remember, I want the thing on top, and this is not recursive. So this is a set containing A. There's only one thing in it, the set A. Yes, if it was equal to the set A, comma, the set B, with brackets, that would be 2. Okay. True or false? If A equals AB and B equals BA, then A equals B. That's true. Why? Order doesn't matter. Order in sets does not matter. Now, we will have things where it does, but those aren't sets. Those are lists. Well, lists are sets, but they're special ways of setting up sets in a way that you can distinguish between which one's first and which one's second. So we will have those. We'll have things that are ordered, but this is not one of them. Plain sets are unordered. Does 3 equal the set 1, 2, 3? That's false. 3 equals the set 0, 1, 2. Not 1, 2, 3. Okay, so 1 to 5, how do we feel about that one? Well, because this is the definition. 3 is defined as 0, 1, 2. Right? 0 is defined as the empty set. 1 is defined as the set containing 0. 2 is defined as the set containing 0 and 1. 3 is defined as, that's backwards. 3 is defined as the set containing 0, 1, and 2. So if this had said 0, 1, and 2, that would have been true. But it didn't. It says 0, 1, it says 1, 2, and 3, and that's false. Yes, the number 3 is the set of things that a natural number is the set of natural numbers that came before. Yes. Where is 3 equal to 1, 2, 3? It's 0, 1, 2. We did this. This was the thing we did last time. Class notes, class 1A. The von Neumann natural numbers. We have 0 is defined as the empty set. 1 is defined as the set containing empty set, which equals the set containing 0. 2 is defined as the set containing an empty set and the set containing the set containing and the set containing the empty set, which is 0 and 1, and so on and so on and so forth. Okay. All right. Right. So if something is defined as, that means from now on it's equal to. Someone's asking about that thing. So this defined as notation, later it'd be equal to. Because I defined it as, now it's equal. It's a subtle thing. It's a way of saying that wasn't equal before, but we made it equal when we're constructing stuff. But now it is equal. Okay. Oops, I don't want to switch to calculus. I want to go back to the quiz. There we go. Let A be a set, then the empty set is in A. That is false. Example. The empty set is not in the empty set. The empty set is not in the set 1, 2. The empty set is not in the set containing the object A. Okay. All right, so what does that mean? Right, so let's look at this. Why is this true? Okay, let's look at this. If I have a bag containing the orange juice, okay, let's say that this is a bag containing the orange juice. Is an empty bag in the bag containing the orange juice? No, the bag contains only the orange juice. If I have this bag here, it's empty. This is the empty set. It's nothing but an empty bag. Okay? Now, I have my earbuds. I put my earbuds in this empty bag. Now, does this bag contain an empty bag? No, right? It contains my earbuds, but not an empty bag. Now, if I had an empty bag, and here's another empty bag. This one's larger. Now, I throw my earbuds and the empty bag in my empty bag. Now, does this new empty bag contain an empty bag? Yes. There's an empty bag in there. This bag now contains the empty bag and my earbuds. Okay? But if I take the empty bag out, now it just has the earbuds. So, an example of a set with an empty bag in it would be the empty set is an element of the set containing the empty bag. Right? This right here is a bag inside a bag. Does the outer bag contain an empty bag? Yes. 1 to 5, how do we feel about that now? Okay. Is the empty bag a subset of A? That's true. No, it's not a part of it. The empty bag is not a part. So here, this is an empty bag inside of an empty bag. So yes, there is an empty bag inside of a bag containing an empty bag. But there's not an empty bag inside of an empty bag. Right? This is a set with nothing in it. This is an empty bag. Is there an empty bag inside the empty bag? No, there's nothing inside the empty bag. But there is a empty bag inside a bag containing an empty bag. But is an empty bag a subset of A? And that's true, right? Because this set, right? If I put in this bag my earbuds and this what is this thing? This SD card adapter, right? I now have a bag with two things in it. Now, what are the subsets? Well, if I have an empty bag, right? An empty bag, everything in an empty bag is also in a bag containing the SD card and my earbuds. Yeah, so if A was empty set 0, 1, and 2, then yes, the empty set would be an element of it because I'd have an empty bag inside that bag. Right? Other subsets. Well, the bag containing my earbuds, every element of a bag containing my earbuds, which is my earbuds, is in the bag containing my earbuds and the SD card. Okay. Name one thing you found about the first lecture. Okay. Any other questions? Okay, cool beans. Are the subsets of a set elements of the power set? Yes. The subsets of a set are exactly the elements of a power set. That's what they are. Okay. Three C was false. The empty bag is not an element of every set. There do exist sets where the empty bag is not an element of the set, right? Because the empty bag is not an element of the empty bag. But the empty bag is a subset of every set. Okay. All right, let's check this out. Yes, so K A is representing any set on every set. Well, it's not representing every set, but it's representing any set. It's every set. Okay. There we go. Okay. Now we're back. Let's talk about what we're going to talk about today. So, what we're doing is we're going to talk about the binomial theorem today in counting in the rule of and. Because what we want to do is we want to address subsets of a certain size. Okay, so let's start with kind of a problem. I did not get this started because I was playing with my microphone. Little dead air time. Talk amongst yourselves while I find my example. What did I do with my example? Ah, there it is. Okay, so I have this problem. And the problem looks like this. I have all of these, the book problems to review, yeah. So what we're doing tonight, what we're doing for the next two lectures is we're going over chapter 9, but we're doing them backwards. So today we're going to do 9.5 and 9.7, and then 2A, so on Tuesday, we're going to do 9.2 and 9.3. And all of this stuff, so these are the problems in the book here, and you'll see them again. Okay. So here's the problem that we have. I have all of these peer leaders for calculus, right? This is what I was talking about before. And we've got 2 training times and we've got 31 peer leaders. And I have to find 2 training times that will work for these peer leaders. Okay? So here's the situation. I have a set of training times and a bunch of peer leaders. Okay? Now, the training times that are possible are, let's see how many there are. There are, let's see, 27, it looks like. Now, okay? So here, I made them fill out a doodle poll. Okay? And this is what I got. Okay? I had them fill out a doodle poll. And you can see up here the times. Let's make that work. So you can see up here the times. I've got Monday at 8, Monday at 9, from 9:30 to 10:45, Monday from 11 to 12:15, and so on and so on and so forth. And then the same thing happens on, I've got a bunch of Tuesday times, I got a bunch of Wednesday times, and I got a bunch of Thursday times. Okay? And then these are all my peer leaders. Okay? Now, I had them fill out a doodle poll. So 1 indicates that this peer leader can make this time. And a 0 indicates that this peer leader can't make it at that time. So 1 to 5, how do we feel about the setup of the problem? I need to find 2 times so that everyone can attend. 1 of them. Okay? So everyone needs to go to a training, and I've got 2 trainers, right? I could set up 2 training times. All right? And I need to set up these 2 times so that there is a time when every peer leader can show up. Okay? That's the problem. Okay, so what am I going to have to enumerate over? What is this set? Okay? So let's call the set A. All right? Let's call times. Let's just call it times, okay? So we have a set times. Okay? And the set times is as, let's see. All right, so in the set of times, let's see, we've got 26, 25, 26, 27, 28. We've got 28. We've got 28 possible times. Okay? All right, and then I've got all these peer leaders, but what I need to do is I need to enumerate over the pairs, the unordered pairs of times, checking to see if each peer leader can make one of those 2 times. All right? Okay. So the question I have for you is how many elements are going to be in this loop? So how many unordered pairs must I check? Okay. Notepad++. This should have been already open, and it wasn't. So how am I going to do this? Let's see. I have this set up already, and let's see. Problems, no. Workspace. Discrete math class. Nope, it's not our problem set. It's a class code, and it's not here. Should be in workspace. Workspace peer leading. Here we go. Scott. Workspace, peer leading, utility, check times. Okay. No, this is an actual real world problem. I don't write this much code for something that's not a real world problem. I just changed the names. So here's what it does, right? I wrote a little function here. And what I'm going to do is I'm going to check. I'm going to input a bunch of columns. And then what I'm going to do is I'm going to check each pair of columns to see, and then I'm going to print the peeps who can't work in either of those times. Okay? So this is in workspace, peer leading grade, scripts, utility, I think. No, just utility. Okay, so let's see. We're going to do check times.php, and then I need the path to my Excel spreadsheet, which is not that one, not that, oh, it's that one, which is discrete math class. Let's see. Yeah. So we need discrete math class. Open documents first. Docu. Why is that not working? Oh. Because I'm not there. Home/documents. There we go. Discrete math class, class code, doodle, daily tunes. All right, so now it's going to search. And as it searches, notice what it did here. It ran over every pair of times. So my question was, how many pairs did it check? Right? And then it said, oh, you get, it enumerated who couldn't make it and all this stuff. Okay? So 1 to 5, how do we feel about what this problem's asking here? And I want to know how many pairs, right? Because I did Tuesday at 9:30 and Wednesday at 9:30 here. But as you can say, it says Tuesday at 8 and Thursday at 5. And it just went all the way through, all the possible pairs. Why do I care about this number? Well, I care about this number because if I'm accessing a database, I don't want to thrash my databases because that's just rude. Okay? So I want to know how many operations I'm going to be running on my computer. Okay? Well, let's give this thing a name. We're going to enumerate. We're going to call this, we're going to enumerate. All right? So we're going to call this. So let definition. Let A be a set. Okay? Let A be a set. A choose N, or A choose K, I'll use K. A choose K is the set of K-sized subsets of A. Okay? And this is read okay? So let's say example. Okay? Let's let S equal the set A, B. Well, let's give him 3. A, B, C. Then A choose 2 equals the set of 2-element subsets. So I want the unordered pairs. Okay? So how do we feel about this? 1 to 5. Oops, not there. Right? I'm sorry, that should be an S, not an A. So this is S choose 2. S choose 1 would equal the sets A, B, and C. The sets containing the singletons. S choose 0 equals the empty set, right? Because these are all the one element subsets. These are all the 2 element subsets, right? And then S choose 3 would be all of the 3 element subsets. And there's only one of those. Okay? This is not a permutation. This is completely different than a permutation. Okay? So order doesn't matter here, right? I don't care about the order. These are just sets. This is the number of subsets I have. I'm sorry. This is the size. This number on the bottom represents the size of every subset. So I want all the 2 element sets. Okay? Right? So S choose 0 would be all of the 0 element subsets. Well, there's only one of those. It's the empty set. So let's give a more concrete example. If we're playing 5-card straight poker, let's get a new deck of cards. It's a new semester. We should have a new deck of cards. Yes, that is a box of new decks of cards. I am that big of a geek. But I trimmed my nails, and now I can't open my deck of cards. This is what I get for trimming nails. Okay, so let's take our new deck of cards. A brand new spanking deck of cards. We don't need you. We don't need you. Hey, look, it's me. All right, so I have a nice deck of cards. Now, how many ways are there to deal a hand of straight 5-card poker? Okay? This is 5-card poker where I'm dealing 5 cards to each individual player. How many ways, or what are the possible hands? Not how many ways, what are the possible hands that you can get from this deck? All right? So my deck of 52 cards, right? What are the possible hands? What is the set of possible 5-card hands that I can deal from this thing? What would I call that set? It's not 2 to the 52. 2 to the 52 would give me the size of the power set. I don't want that. I want to know how many ways. I want to know what is the set. Okay? So example. Let C be a standard 52 card deck of playing cards. What is the set of all possible 5-card hands? And remember, in poker, the order doesn't matter. That's right. It's S, choose 52. I'm sorry, C, choose 52. Right? Not 52, I'm sorry. C, choose 5. I don't know why I said 52. C, choose 5. That's right. Okay, so this is all the ways that I can deal a hand of poker, right? What are these? What's in here? Let's look at C choose 5. What's in here? Let's see. I've got the king of clubs. Let's see. Here's a hand. Oops, it's all over the place. It's not a very good hand. I dropped them. New cards are always, slippery. Right? So here's a hand. I've got the queen of diamonds, the king of diamonds, the jack of clubs. I'm sorry, the jack of hearts, the 10 of hearts, and the king of clubs. Okay, here's a hand of poker. Why is it doing that again? Right, here's a hand. Okay? That is the same hand. The order doesn't matter, right? This is the same hands. It's still a pair of kings and some junk. Okay? However, this is a different hand. Right? It's 5 cards, but one of them's different. Okay? So those are 2 different elements of C choose 5. Okay? How do we feel about this 1 to 5? Sorry, I've got the thing on the wrong... Oop, there went the cards again. Oops, that didn't work. Sorry, trying this again. There we go. Okay. All right. How many 5-card subsets are there? Or no, what are the 5-card subsets of this? Okay? Now, no, C is not the number of hands. C is the set of cards. So C choose 5 is a set. Okay? So let's look at what some of these elements are. Right? I can have the set of ace of hearts, ace of diamonds, king of hearts, king of diamonds, and king of spades. Right? And what do I have? This full house here is an element of C choose 5. Now, the number, no, C does not equal 52. C equals the set. C is the set, not the cardinality of it. Okay? C is the actual set. 52 choose 5 is coming in just a moment. Now, definition. Let N and K be natural numbers so that N is greater than or equal to K. Okay? This should be in purple because it's a definition, shouldn't it? Oops. Okay. n choose k is defined to be, right? So these are numbers. Is defined to be the cardinality of A choose K, where the cardinality of A equals N. Okay, so what have I just said there? So here, for example, (52) choose 5 counts the number of possible 5 card hands from a deck of cards. Okay? Where A is a set, so that. So what I'm doing here is I'm defining a number, right? 52 choose 5 counts the number of possible 5 card hands of poker, right? Because the size of C equaled 52. So the size of C choose 5 equals 52 choose 5. Okay? 1 to 5, how do we feel about that? Okay? And this is what we normally think of this binomial, but the kind of standard, or the new standard, I should say new, it's about 10 years old now, is to actually write the sets like this. Just like we wrote 2 to the C to be the power set, we write C choose 5 to be the set of 5 element subsets. And then we define the cardinality in terms of the set. It's a little weird. Okay? So for our early problem, 28 choose 2 would be the number of pairs of times in the previous example. Okay. K is not a subset of N. K is a number. Let A be a set, and I'll put that in K be a natural number. I should write that in my definition. Okay. All right, well, what would those values be? Well, let's figure out some of them, okay? Some of these values. Okay, let's figure out some of them. So let's do 52, choose 1. Okay, so how many ways are there for me to deal you 1 card? How many different 1 element subsets are there? There's 52. And do you believe me that N choose 1 is always equal to N? We'll do a little generalization on this side here. Do you believe me? Okay. All right. Now, how many ways are there for me to give you 52 cards? Right? 52, choose 52. How many ways are there for me? How many subsets containing 52 cards are there? How many different ways are there for me to give you 52 cards? There's only one. Okay? Now, if I give you 52 cards, if I give you one card, okay, how many cards do I keep? If I give you one card, how many cards do I keep? So, every time I count the ways to give you one card, I've also counted a way for me to keep 51. How do we feel about this 1 to 5? Every time I count a card, I've also counted the number of ways for me to keep one. I mean, for me to keep 51. That means, okay, every time I count a card, so what's 52 choose 51? Exactly. 52 choose 1 is equal. 52 choose 51 is equal to 52 choose 1. How do we feel about that? Okay. If I count the number of ways, every time I give you a card, I keep 51 cards. Okay? So every time I give you a card, I count the number of ways. So every time I give you a card, I count a way to keep 51. Okay? Therefore, 52 choose 1 must be less than or equal to 52 choose 51. Do you buy that? Every time I give you a card, I count a way to keep 51 cards. So the number of ways to give you one card, right? Since every time I've counted one of these, I've counted one of these. Right? Every time I give you a card, I count the number of ways to keep one. I'm sorry, I count the number of ways to keep 51. Now, every time I give you 51 cards, I count the number of ways to keep one. Okay? So every time I count the ways, every time I count a way to give you one card, I also count a way for me to keep 51. Therefore, I must at least have 52 choose 1 ways to count 50 to items in 52 choose 51. But the same thing holds in reverse. So these must be equal, right? 52 choose 1 is less than or equal to 52 choose 51, and 52 choose 1 is less than or equal to 52 choose 1. And the only way that holds is if they're equal. And yes, in general, n choose n minus 1 equals n choose 1 equals n. But it's even more powerful. But wait, there's more. Why is that up? Sorry, that's up. Oh, shoot, I'm dropping everything. Sorry. But wait, there's more. It's not Pascal's. I'm trying to remember which one is it called. There's rules, there's identity, and there's a law. And that's annoying to me. We'll just call it the mirror principle. It's Pascal's something. I don't remember what Pascal's it is. But wait, there's more. N choose k is equal to n choose k, n minus k. I think this is called Pascal's symmetry. But that's what you've just shown. Now, the wager is a philosophical argument, which is very fun. Okay, so I've got a bunch of things. Okay. Yes, this is part of Pascal's triangle, but this is the symmetry of the thing. Speaking of which, what does that have to do with the binomials? By the way, this gives us the fact that 52 choose 0 equals 1. There's one way for me to give you no cards, and it's the same as the number of ways for me to keep all the cards. And in general, we have that property in general. N choose 0 equals 1. Okay? So we have these little things that go with it. Now, what does this have to do with Pascal's triangle? Okay? So let's talk about the binomial theorem. All right? This is a big heading. Okay? So, this is actually this is a big deal. This is actually one of the theorems that holds together mathematics. Okay? And it's one of the core. Oh, I'm so touched by what you guys are saying in Twitch. And it's one of the core. I'm crying. Look at me. You've got me all messed up. And it's one of the core pieces of mathematics. It's one of the things that glues math together because it relates a whole bunch of things relates a whole bunch of things in number theory to a whole bunch of things in combinatorics to a whole bunch of things in calculus and everything. It's really a piece of glue. All right, it's one of the most important theorems in mathematics, believe it or not. And it's actually kind of simple. So let's look at what happens if I do a plus b cubed. How do I multiply this out? All right. So I've got a plus b times a plus b times a plus b. And that's going to equal the following. That is going to equal a cubed plus 3a squared b plus 3ab squared plus b cubed. Okay, now how do I know that? If I multiply it out, right? I'm going to take this a and multiply it by this a and multiply it by that a, right? So I'm going to get a cubed. Now, for the next step, oops, I want this to be in blue. Now, for the next step, what am I going to do? I'm going to take this a, and I'm going to multiply it by that a again, but then I'm going to multiply it by that b. So I'm going to have a squared plus b. 1 to 5, how do we feel about where we are now? Okay. Now, for the next one, I'm going to take this b. That should not be a plus, it should be a times. Thank you. Now I'm going to take this b, and I'm going to multiply it by that a and then that a. And I wind up with a squared b. Now I'm going to take this b, I'm going to multiply it by that b, and then I'm going to multiply it by a. And I'm going to get b squared a, or ab squared. Now I'm going to take this b, I'm going to multiply it by that b, and I'm going to multiply it by that b. So I'm going to get b cubed. All right, now what am I going to do? B, A. So I get A, then that one, then that one. Then I went this one, then this one, then this one. Then I went this one, and this one, and this one. Okay, so I did all these. Now what am I going to do? How do I proceed? Which ones haven't I done yet? I haven't done ABA yet, right? So ABA is going to be a green one, right? A, B, A. Now what? A, B, that was ABA. A, what? Which ones haven't been done? I'm missing two more. I need to do B, B, A. Did I do that one? I did that one. Did I do A, B, B yet? That's right. A. I did A, B, B. Yes. I did A, B, A, right? Now I'm going to have another one of these. A, B squared. And then another one of these. Okay. I should have left them out of order. I'm sorry I did that. Let's do this real fast. I'm sorry. I should have done this out of order. Rewind. I shouldn't have combined the terms like this. rewind, cut everything that just happened. You guys have already told me. So let's just do them like this. So I've got AAB plus ABA plus BAA. Note for next year, present it this way. Plus ABB plus BAB plus BAA. Nope, that should be BBA. Plus BBB. Okay, are we back on the crazy train? How do we feel about that now that I did them in a better way? Better presentation of this material. Okay. So what did I do? How did I get these terms? Right? So consider the ways to choose A. How many ways are there to choose 3 A's? There's 1, right? How many ways to choose 2 A's and 1 B? Really, how many ways are there to choose 2 A's and then I pick the B? How many ways? Oh. Sorry, this should be 3 choose 3, not 3 choose 1. How many ways are there to choose 2 A's? That should be 3 choose 2. There are 3 A's total, and I chose all 3 of them. How many ways to choose 1A? 3 choose 1. How many ways to choose 0 A's? 3 choose 0. So, A plus B cubed equals 3 choose 3, A cubed, B 0. I chose 3 A's, and thus I did not choose any B's. Plus 3 choose 2, A squared, B to the first. I chose 2 A's, and as a consequence, I had 1 B. Plus 3 choose 1, A to the first, B squared. I chose 1A, thus I chose 2 B's. Plus 3 choose 0, A to the 0. I chose no A's, and I choose 3 B's. How do we feel about that? 1 to 5. Okay. How about A plus B to the 4th? Well, how many ways are there to choose 4? There's 4 things to choose from, right? There's got to be 4 possible terms. a to the fourth, b to the 0, a cubed, b to the first, a squared, b squared, a to the first, b cubed, a to the 0, b to the fourth. Now, how many ways are there for me to choose 4 a's from a set of 4 possible a's? One. Before choose 4. I'm not interested in the 1. I'm interested in the 4. There's 4 ways for me to choose 4 a's from the set of 4 a's. From the set of 4 terms. Here, I had 3 terms, so there were 3 possible a's, and I chose all 3. Here, there were 3 possible a's, and I chose 2 of them. Here, there were 3 possible a's, and I chose 1. Here, there were 3 possible a's, and I chose none. How's that? 1 to 5. Now, a plus b to the fourth equals a plus b times a plus b times a plus b times a plus b. I have 4 possible a's. There are 4 a's I can choose from. Okay? The first term, I chose all 4 a's and thus chose no b's. On the second term, how many ways are there to choose 3 a's from this set? I could choose this one, and this one. I could choose this one, and this one. I could choose this one, and this one. And I could choose this one, and this one. So there's 4 choose 3 ways to choose 3 a's. Plus 4 choose 2 ways to choose 2 a's. Plus 4 choose 1 way to choose 1 a. Plus 4 choose 0 a's to choose 0 a's. How do we feel about that? I have 4 possible a's, and I've enumerated the number of ways to choose. You know, I could choose 4, I could choose 3, I could choose 2, I could choose 1, and I could choose 0. Theorem. The binomial theorem. Okay? And this is the big one. This is the most important theorem. If there's one theorem in the class that's the most important theorem in the class, this is it. We're going to see this again and again and again and again and again and again and again. We are choosing from these sets, right? I've got this. I can choose the first one, the second one, the third one, and the fourth one. I've got 4 possible ways. I've got 4 possible ways, 4 possible things to choose my A's or my B's from. So this is the binomial theorem. Let A and B be some sort of number. Okay, and we'll get into what I mean by some sort of number later. But basically be numbers. Okay. Let n be a natural number. I actually want it to be a positive integer. If it's 0, who cares? It's just 1 period. Okay? Then, a plus b to the n equals, and choose 0. Oh, sorry, n choose n. I'm doing n choose n. N choose n, a to the n, b to the 0, plus n choose 1, a to the n minus 1, b choose 1, plus dot, 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 plus, right? I mean, I could keep going. N choose 2, a to the n minus 2, b squared, plus dot, 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 plus n choose n minus 1, a to the 1, b to the n minus 1, plus n choose n, a to the 0, b to the n. Okay? 1 to 5, how do we feel about that? Yeah, n choose n minus 1, a to the first, b to the n, plus n choose n, a to the 0, b to the n. What's the proof? Well, oops. Shortest proof in the book. And that's it. The binomial theorem is just an extension of this combinatorial idea that what I have is, right, that I have this set. I have a set of n things. I have a set of n a's, right? This is a1, a2, a3, a4, a blah, 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 blah. And I simply, if I want to get the coefficient in front of n choose k, right? I just pick it. I just pick the number of ways to choose it. Okay. All right. So next time, I'm 5 minutes over. Sorry about that, but we had a new toy. Next time, computing the binomials. And then we're going to do lists as well. Okay? So that'll be next time. Now, a little bit of business. Tomorrow at what time is the thing? At 5 p.m. is the help session for problem sets. So if you're having problem getting PHP to run, I'll be on Discord at 5 p.m. and we'll talk about how to get PHP to run. Are there any questions about that? And and I'll help you get it. You guys can help each other and all those other things. Any questions, comments, issues, suggestions, thoughts? Okay, well that's it for today. So this is problem set 1. To get PHP running, because that's the thing we're going to use to connect the code to the computer. And you're not supposed to know PHP for this class. I'm assuming you don't know how to use PHP. Okay? I am going to help you use PHP but we're not really interested in learning how to use PHP. We're interested in learning the connection between code and math and code. Okay? So that's the whole thing. If you want to read over for the week, if you want to get ahead, we're going to be doing 9.2, 9.3 next time. This time we did 9.5 and 9.7. There are the problems in the book. Obviously, this will be posted. Also, if you turn to that second book on Canvas, so the Jenkins book. Can I pull it up here without messing up everything? Let's see. Yes. So if you pull up the Jenkins book, you can find the link to that right here. That'll take you to the library where you can find that book. This is section 2.3 in that Jenkins and Stevenson book, who also has a very nice presentation of this. Okay, any questions? Yeah, so the notes assignment, there's no need to make a notes assignment for the Friday thing. The Friday thing is completely optional. It's just help. Okay? The problems are for app. Yes. Please, if you're so there's a question, can the notes be in PDF format? Please put them in PDF format. It's exporting from docs is very easy. Please just do it. It'll make our lives simpler. We really do prefer PDFs. Any other questions? Okay. Well, that's it for today. I'll see everybody. I'll see those of you who want to work on the thing tomorrow. You'll see that there's a rubric for the notes assignment on the thing. All right.